Hey everyone, this is Doug Hennick, Product Manager for the Helius product line, and this is What's New for Helius PFA 2017. Advanced materials are becoming more and more prominent in multiple industries due to their high strength to weight ratio and their high stiffness to weight ratio. So for this release, we've really been focusing on two materials, and that is plastics and composites. And as we begin to push the envelope of structural performance with these materials, typically we also start to increase the cost of the materials. That means that simulation is going to become very important so that we don't enter into costly design cycles. This specific release, the 2017 release, has really been focused on two materials. The first of those being plastics, which include unfilled materials as well as fiber reinforced plastics, and also composites. So these are continuous fiber composite materials. These can be UD, they can be woven laminate materials as well. And we've been interested in focusing on mechanical simulation of these two materials. That is, initiating and propagating material nonlinearity and failure. So let's take a look at what we've been doing for simulating plastic materials. Helius PFA allows users to map data from an Autodesk mold flow simulation to structural FEA. The data includes manufacturing data such as fiber orientations, residual strains, and material properties. You can then map that data to your structural mesh, such as ANSYS and Abacus, to be included in your structural finite element simulation. Autodesk Helius PFA uses the data mapped from MoldFlow in the structural simulation to predict and propagate material nonlinearity at the fiber and matrix level. This is definitely a multi-scale solution. This allows users to include the anisotropic nonlinear response of the material in the structural model and accurately represent the material at the microscale level. It also allows users to predict and propagate rupture of the material in nonlinear mechanical loading so that we can understand what happens if the part does fail. So the first piece of functionality that we added for Helius PFA 2017 is structural assembly support. In previous versions of Helius, users were only allowed to map data from MoldFlow to a structural mesh for one component in an assembly. We have now changed that and allowed users to map data for multiple components in an assembly within Helius PFA. For example, this pedal model has an arm and a base, and they are connected together with contact in a structural assembly. Now in Helius PFA, users can map data for the base and the pedal separately from different MoldFlow studies and include that manufacturing data in the structural simulation. We have also added some functionality to include compressive material responses. So whenever we have multiple components in contact within a structural assembly, that typically means that one or more of the components is going to be in compression. For example, on the screen, the pedal has a toe lift load on it, which means that the areas in red would be tension and the areas in blue would be compression. When a material goes into compression, though, we typically don't see a large failure rupture or rupture event in which the load carrying capability of the material reduces instantaneously like we do in tension. Really what we see is the material begins to lose load carrying capability, as we're seeing in the fourth quadrant on the plot. And once it loses load carrying capability, it continues to plasticize at some reduced load level. This means that we have to capture this response accurately because we need to ensure that we're capturing the energy absorbed by the material. So in 2017, we have added the capability to differentiate between tension and compression within Helius PFA. If users do not have compressive data, we will assume a compressive response so that we can more accurately represent that material and we do not instantly rupture the material during the simulation. We have also added some functionality for weld line strength prediction. Within Helius PFA, we can now map 3D weld surface data from MoldFlow to the structural simulation. Typically, users like to map weld lines, which is shown on the right-hand side of the screen. Now, MoldFlow does output weld line locations, but these are more for aesthetic purposes. What we're really after are the 3D weld surface locations after they have formed and moved due to the packing phase. And that's what Helius PFA maps. So you can now run a mold flow simulation and map the 3D weld surface locations after movement to the structural mesh so that we can accurately capture where those weld surfaces have moved to. In addition to allowing the mapping of the 3D weld surface, we have also developed a weld line strength prediction formulation within Helius PFA. This prediction and the mathematical model is shown on the bottom of the screen. It is a long equation. The strength prediction is a function of the temperature history and the pressure history and the flow front meeting angle of every single point in the weld surface. So Helius will survey all of the points in the 3D weld surface, look at the history from the molding simulation, and come up with a strength reduction factor for that material. What we're showing on the screen is a comparison between experimental results and simulated results using Helius PFA. We've done this with no weld lines. So this is a single gated dog bone, and that's shown with the black dash line for experimental and then the blue solid line for simulation. And we've also completed this for a model with a weld line. So this is what we call a double gated dog bone, which has been injection molded from each side, and a weld line has been induced in the middle of the model. The load carrying capability is significantly reduced. First, because this is a fiber reinforced material, which means that the fibers are not crossing that weld line boundary. They are typically randomly aligned or aligned with the surface, perpendicular to that surface, or parallel to that surface. And then also because we don't have mixing of the polymers, so we also have some additional strength reduction due to the temperature and pressure history, as well as the flow front meeting angle. So you can see the simulated response using Helius PFA matches that of the experimental very well. And also when we're showing the failure mode, which is shown on the right-hand side of the screen, comparing Helius to experimental, we're doing a great job there as well. Now this does require input data for us to be able to calibrate these strengths. If you do not have the input data, we can always just assume a constant strength reduction for the model. But if you do use this model, we do have a varying strength reduction across the model, and Autodesk is going to be able to test those capabilities and coefficients for you as well. As far as productivity is concerned for the plastics workflow within Helius PFA, we are significantly expanding our materials database and also including nonlinear mechanical testing for unfilled and fiber reinforced materials. So now Autodesk can test your materials and we can include them in the mold flow database. What that means is the users can run the mold flow simulation and all of the nonlinear mechanical data will automatically be transferred over to Autodesk Helius PFA. The users do not need to enter additional nonlinear mechanical data as it will already be present in the mold flow materials database. So we believe that everything hinges on accurate material data. We are able to test the nonlinear mechanical data for our users and include it in the database, and we will be continually striving to populate the database with more nonlinear mechanical data so users do not have to keep entering it. It will just automatically flow between our products. We have also added some capability for confidential material data, and this has been a request for quite some time in the mold flow world, and this is very important when we're talking about nonlinear stress strain data. So now users can use the mold flow data classifier and they can suppress confidential data such as stress strain curves and also Ramberg-Osgood parameters, which are used by Helius PFA for nonlinear mechanical simulation. If those data fields are set as confidential, the data will not be displayed to the user. It will have a confidential field written over it, and there will be no information written to the solver. So the information will stay confidential from the users for as long as the material is in the database. Material suppliers can perform this action on their own and provide the databases to the user, or they can provide the databases to the team for inclusion in the database. The final piece of technology that we've added to Helius PFA for the 2017 release is a mesh-sensitive failure model. Now, this is really important when we start talking about failure of fiber-reinforced plastics specifically. So, on the screen is a biaxial coupon. This is a fiber-reinforced plastic, and we pull on the tabs in different directions. Now, next to that coupon, we're looking at the through thickness direction where we have the axis labeled Z. And what we're interested in determining is the dependence of the ultimate strength of the coupon with the number of elements through the thickness of Z, or through that axis Z. And we've actually plotted this dependence on the bottom of the screen, where we have the strength of the coupon as a function of the elements through the thickness. So we plotted these two together. You can see that in fiscal year 16 or FY16 release, we had a large dependence on the number of elements through the thickness, and we'll describe why this is on the right hand side of the screen. So if you look at the A11 component of a fiber reinforced plastic orientation tensor, it varies with the green line shown on the right hand side of the screen through thickness. If we have one element through the thickness, you can see if we had one integration point in that element, we would be capturing the very middle, or the dip in the curve for A11, and we would have a low strength because we would have a lower alignment. But if we increased the number of elements through the thickness to 2, we would now capture the response near the edges of the dip, and we would have an increase in strength. Similarly for 4, we would now have an increase in strength as well, and eventually we would be able to increase the number of elements through the thickness enough so that we would level off, and you can see that is a number of elements through the thickness of 12 and more. We have converged on a solution. Most users do not want to run 12 elements through the thickness for a structural model. That is quite a lot of elements, and your model size begins to grow exponentially. So what we've done in Helius PFA is added the capability to survey the fiber orientation tensor as a function of elements through the thickness or orientation. And so now we can actually take that into account when we're predicting rupture and propagation of rupture. And now in FY17, as you can see in the blue curve, we have a much less dependence on the number of elements through the thickness, and you can see that we converge on an acceptable solution much quicker. Somewhere around 4 elements through the thickness would suffice in this case. So now let's take a look at what functionality we've added for composites workflows. Again, Helius PFA is an add-on to Abacus and ANSYS for structural simulation of composite materials as well as plastic materials. And for composites, we've added some new functionality specifically for continuous fiber composites. The first of that is support now for Autodesk Nastran. So Autodesk Nastran can now leverage Helius PFA in the background to predict initiation and propagation of failure for continuous fiber composite materials. The workflows for including Helius PFA with Nastran are shown on the screen. You can now export a model with FEMAP. You can add the new cards to the Nastran deck, run it in the Nastran solver, and then post-process in FEMAP. Similarly, you can do that with Autodesk workflows such as the Nastran editor. And on the right-hand side of the screen, we are showing a damage plot of a continuous fiber composite laminate. As loading increases, you can see damage spread from the whole edge and continue, and then we have some ultimate failure propagating from the whole edge as well. We've also added some new capabilities for woven material models in the background of Helius PFA. So the first thing that we've done is increased the efficiency of our micromechanics models. Now we're able to simulate 4, 5, and 8 harness satin materials on the fly within Helius PFA, which means that characterizing and utilizing woven materials with Helius PFA is now even easier due to these efficiency improvements. And we've also included nonlinear shear behavior for woven composites. Woven composites have a very large dependency in nonlinear shear. We see a lot of nonlinearity, and we've now included that behavior for woven composites as well. So that's what's new for Autodesk Helius PFA 2017. I hope that you all try the software and ask us any questions and feedback. Thank you.